Okay, so a major thing that we can do with the coalescent is to look at the distribution of frequencies of mutations. So we'll often see this written in terms of, so this will be the frequency of the rare allele. So let's start with some sequences. Right, so one thing we can do with data like this is we can summarize the frequency at which we see the mutations. Okay, so in this these four sequences, we notice at this site we have 3 that have C and 1 has T. So that would mean that our less frequent allele, which here is T, is present at 1/4. Here we have 2 with G, 2 with A, and so this would be 1/2. And here we have 2 with C and 2 with T. So that would also be 1/2. And so we could summarize that. So if this is the frequency of mutations from 0 to 1, so we could summarize the frequencies of our rare alleles here. This would be the number, let's see, the number of sites. So then we would see that at 1/4 we have 2 sites, and at 1/2 we have 1 site. Okay, so that would be this would be a very simple graph of things. Of course, we want more sequences so that we have better estimates. So they're not all 1/4, 1/2. And we'd like more sites so that we can get a sense of the shape of things. And so something that you'll frequently see is the frequency site distribution. So people will show frequency site distributions like this. Now, these are very important because they allow us to detect the action of selection, or selective mating, or population subdivision. And so the way that this argument will go is basically like, so if you want to ask, are sites, are non-synonymous mutations that are occurring in the population, are they generally neutral, are they generally positive, are they generally negative? What you can do is you can take the theoretical distribution of what you'd expect here, and you can compare it to your actual observed distribution. So let's look a little bit more at what that looks like. So let's say that our theoretical distribution looks like this, where we should have a lot of sites where the rare allele is at low frequency, and fewer sites where it's at high frequency. And I'm going to correct one thing here. I said that what we're graphing is the rare allele. So obviously the rare allele can't be at frequency 1, because by definition the rare allele can only be between 0 and 1/2. So let's just correct that. Okay, so if this is the theoretical distribution, then we can look at our real distribution. And so if we see something like this, so what that would mean is that, notice that our real distribution has more low frequency mutations than we'd expect, and fewer high frequency mutations that we'd expect. So this is exactly as we'd expect if selection is driving these things out of the population, keeping them at low frequency, not allowing them to get to high frequency. And so we could then infer from this that selection is acting against this class of mutations that we're studying. If we see the opposite, fewer low frequency mutations and more high frequency mutations, then we can infer the opposite, that selection is favoring, is promoting these alleles into the population. Okay, so what we're going to start to do here is think about how we can use the coalescence to figure out what our distribution of frequencies are. So we're not going to get all the way through this, in part because it gets sort of beyond what I think we want to spend our time on, unless you want to, in which case I can point you to it. But I just want to do one specific class of mutations, and that's the singletons. So singletons, these are cases where we have n minus 1 of our sample has one allele, and then one of our samples has a different allele. So here, n minus 1, 3 have the C, but 1 has the T. And so my main goal here is first to show you something that, that actually is a major output of the coalescent, but also to show you sort of how we can start to use these coalescent, these very dry mathematical equations to try to actually to generate some particular expected results.